Thank you very much. Thank you very much for the invitation. Um, yeah, so as I was saying, I kind of forgot I was giving this talk until a few hours ago. So I will be improvising for most of this talk, which means you should feel very encouraged to interrupt me. Um, but yeah, at least for the first 45. So first I speak for 45 minutes, then we take a break. Is that
Yes.
okay? Um, um, for the first 45 minutes, I'm just going to be talking about some background. So first of all, I should define the objects in the title. Um, um, the systole of a closed hyperbolic manifold M. So by that I mean a closed manifold of constant sectional curvature equal to -1 is, but I'll denote it sys M, is by definition the length of a shortest closed geodesic in M. I say a shortest because in general there will be many. And a shortest geodesic exists by compactness of M. So this is a well-defined and positive quantity. And maybe I'll also define this set. This will be the set of systoles of closed hyperbolic manifolds of dimension n. And the result I would like to discuss today, it's a very recent work with Junzhi Huang, whom I should have mentioned actually. So this is all Junzhi Huang, is a graduate student at Yale. The result is that this set is dense in the positive reals for every n. So for n equal to 2, this should not be surprising. In fact, in that case, maybe just, I mean, it doesn't matter, but for n equal to 2, this set is in fact the entire set of positive reals, and you will see a proof of this fact in the talk. But for n at least 3, so this result appears to be new even for n equal to 3, which is perhaps a bit surprising because in dimension 3, there are many tools for producing closed hyperbolic manifolds, tools that are absent in higher dimensions, like topological tools, Dane filling, etc. But in fact, the technique is uniform, and I'm going to try to give you a semi-complete proof of this theorem. But first, let's just establish some easy facts about this set Sn. So it's easy to see that this set is unbounded for all n. And this follows from residual finiteness of fundamental groups of closed hyperbolic manifolds. So point is that if M is a closed hyperbolic manifold, then its fundamental group acts by the deck transformation action of the fundamental group of M on the hyperbolic, let's say it's an N manifold, on the hyperbolic space of dimension N, realizes the fundamental group of M as a finitely generated linear group, right? A group generated by a finite set of matrices. So we get an embedding of Pi1M into this Lie group, which is a linear Lie group. In fact, it's isomorphic to this group. So, I haven't defined this group, but so first of all, this group is just the group of matrices of dimension n+1 preserving a Lorentzian form, so a form of signature n1. This group has 4 components, and these are two of the 4 connected components. So if you have a, okay, let's say before I add the say this is a quadratic form of signature n1. The set of vectors in R n+1 on which this form evaluates to -1 is a 2-sheeted hyperboloid. And now this is just the group preserving each sheet. And each sheet then becomes a model for a hyperbolic n space. And this will become relevant later. But the point here is that the fundamental group of a closed hyperbolic manifold is a finitely generated linear group. And so in particular, the fundamental group of such a manifold is residually finite. So really Maltsev is residually finite. And this is to say that, i.e., for every non-trivial element of the fundamental group, I can find a subgroup lambda, let's say, of finite index, excluding gamma. And in fact, once I can find a finite index subgroup, I can also find a finite index normal subgroup. So I can upgrade lambda to a normal subgroup. In fact, in practice, this will be a congruent subgroup. What we're saying is that basically what we're using, what this theorem of Maltsev says is that what it uses is that finitely generated domains, finitely generated rings are residually finite. and then one uses congruence quotients to detect non-trivial elements in the group. And then also once if you have a group that's residually finite, it's also fully residually finite, which means given any list of non-trivial elements, any finite list of non-trivial elements, I can also find a finite index normal subgroup excluding all the elements in that list. So how is this relevant to I mean, justifying this remark? Well, the point is that if I have a closed hyperbolic manifold, given any positive number L, there are only finitely many closed geodesics of length at most L in the manifold. And these closed geodesics correspond to conjugacy classes so a finite set of conjugacy classes in the fundamental group. And now I can pick representatives of each of these conjugacy classes. And if I take a finite index normal subgroup, excluding each of those representatives, I get a finite cover of M whose systole is larger than L. This is a kind of I mean, this is a motif that will appear again and again in the talk, that a finite I mean an abundance of finite index subgroups allows you to construct manifolds with a small systole or with prescribed systole, essentially prescribed systole. But the first very basic fact is that residual finiteness of a fixed of the fundamental group of a fixed hyperbolic manifold gives you the unboundedness of the set of systoles of all hyperbolic manifolds in that dimension. Are there any questions at this point? Something that's less clear maybe is that I mean, it's certainly less clear, is that 0 is an accumulation point of the set of systoles of hyperbolic manifolds of dimension n for all n. So this is maybe not, I mean, even immediately obvious in dimension 2, but I mean, let's justify it first of all. And so what this fact is saying is that there are manifolds of arbitrarily small systole in each dimension. In fact, in dimension 2, something stronger can be said. In dimension 2, we have the following fact: for all epsilon sufficiently small, there is a closed oriented hyperbolic surface of genus 2 and of systole precisely epsilon. We can't hope for anything this good in dimensions higher than 2 by Mostow rigidity. So Mostow rigidity tells you that 2 closed hyperbolic manifolds of dimension at least 3 that have isomorphic fundamental groups are in fact isometric. And the fundamental group is a finitely presented group. So I mean, there are countably many finitely presented groups up to isomorphism. And so there are only countably many systoles of hyperbolic manifolds in dimension at least 3. But in dimension 2, we have this fact. And notice that I said epsilon sufficiently small because I mean, if a surface has large systole, this automatically gives you a bound on the volume. I mean, this is a straightforward exercise. And then in dimension two, um, the volume is essentially the topology. So you can't hope for for fixed topology, um, and small systole. I mean, a large systole, or like arbitrary. I mean, arbitrarily large systole. Um, Okay, and this fact, I mean, there are many ways of proving this. To me, the most elementary thing is to use right-angled hyperbolic polygons. So in the hyperbolic plane, we can think of it as, I mean, one model is the upper half plane model, in which geodesics are lines or semicircles orthogonal to the boundary. Well, you're seeing a portion of the boundary. And now I'm going to construct a one parameter family of right-angled pentagons. So I fix a line. And now I take a circle of a fixed Euclidean size, and I slide it along this ray. And once I decide where to stop, I've determined the pentagon. So you should think every angle you see in this picture will be a right angle, even if I don't draw it. It doesn't successfully. I mean, I don't depict it successfully. Every angle is supposed to be a right angle. Actually, let me make it closer. Now I take the common perpendicular, which will look something like this. And now sorry, this doesn't look perpendicular. And now I dilate this picture at this with center at this point. So and I do it. I mean, by the intermediate value theorem, essentially, I can't. I mean, it's possible to do this so that now in this picture, all angles are right angles, and then here I have a right-angled pentagon. And it was entirely determined by where I stopped sliding the initial circle on that ray, on the boundary. So the point now is that the distance between these two sides of the pentagon is determined by how far I slid the circle. So if I slide it very far, I mean the distance is the ratio, is essentially, I mean, it's related to the ratio, but it's the log, if you want, of the ratio between the Euclidean diameters of those two circles, of these two circles. And so if I slid this circle further, I would get a smaller ratio, and if I slid closer, I would get a larger ratio. But the point is, I can make it as small as I like, and then so now so I've constructed. I mean, for every epsilon. In fact, here you will want to make this epsilon over 2. The hyperbolic distance, I mean, the hyperbolic length of this side, you'll want it to be epsilon over 2. And now, double this picture along that side, so just reflect it so that you get a right-angled hexagon. I can't do that. So now you have a right-angled hexagon here. And now we'll just build by hand a hyperbolic surface using this hexagon. So we have something that looks like this. And now, and this length is epsilon over 2. In fact, do I want it to be epsilon over 4? Yes. Okay, the point is it's small. Probably I'll want it to be epsilon over 4. We'll see. Well, epsilon over 4 will definitely work because this cover will be degree 4. So and now what we'll do is we'll double alternatingly along sides. So let's color the sides red and blue. And first, let's say we double along the blue. Then we get something that looks like this. It's a pair of pants. Maybe I should use blue. No, oh, first I double, okay. And now it's maybe not so clear, but if I double this pair of pants along the red, I will get a genus 2 surface. And this short orthogeodesic that I have here will become a short closed geodesic. I mean, you should, well, okay. I maybe won't, I mean, the picture will look eventually like this. And in fact, for a sufficiently small epsilon, this will be the unique shortest closed geodesic. And this is because, I mean, you can see this because you can show that the lengths of these sides will converge to some positive number. I mean, they won't be getting small. So this is a construction of I mean, surfaces with arbitrarily small systole. Are there any questions about this? So in dimension 3, to my knowledge, so maybe I mean that 0 is an accumulation point of S3. So that there are closed hyperbolic 3 manifolds of arbitrarily small systole. I mean, follows, for example, from Thurston's hyperbolic Dane-filling theory. Basically, if you take a cusped hyperbolic 3 manifold, you can approach this three manifold by closed hyperbolic three manifolds, and in practice, what one does is, I mean, these, I mean, I mean, a torus somehow becomes a closed geodesic, and this closed geodesic will, as you go further in this a sequence of, so you have a sequence of manifolds that are approaching this thing. And as you go further in this sequence, so the systole will be, I mean, this geodesic will be getting shorter and shorter, this core geodesic that you're adding. To my knowledge, this is the first, I mean, the first justification that zeros an accumulation point of S3 is this, I mean, is Dane filling. But there is also an elementary way of doing this, again, using right-angled hyperbolic three polyhedra. Let me give you an example. So in fact, what I'm going to construct now are not closed hyperbolic three manifolds with systole going to 0, but cusped hyperbolic three manifolds with systole going to 0. Forgive me, but I mean, in fact, there's a related technique that gives explicit examples of closed hyperbolic three manifolds with systole going to 0. But the idea is the following. So now I want you to think of your screen as the boundary of hyperbolic three space. So this is the upper half space model, and let's say hyperbolic three space is the space above your screen. And in this model, in this model, geodesic planes are either planes orthogonal to the boundary or hemispheres orthogonal to the boundary. But I mean, it's a bit difficult to draw three-dimensional pictures. So instead, we'll think of the board, or it's not the board now, it's the screen. The screen as the boundary of H3, and I'll just draw, I mean, the traces of these, the ideal boundaries of these geodesic planes. So again, like in the two-dimensional case, we would like to construct, we would like to find a hyperbolic polyhedron with two sides that are very close. And what does it mean for two geodesic planes to be very close? If I draw them so that they're concentric, I draw their ideal boundaries so that they're concentric on the boundary of H3, which I repeat is the screen. Then again, we just want the ratio of the Euclidean diameters to be close to 1. That's what it means for so you should think now that there are two hemispheres. So there's a hemisphere sitting above each circle in this picture. And now we would like to, I mean, okay, if we just take the common, I mean, the exterior of this geodesic plane and this one, and the interior of this geodesic plane, that gives us an infinite volume polyhedron, and a very uninteresting polyhedron. And it's infinite volume because if you're a fly and you're trapped between these two hyperbolic planes, you have lots of access to the boundary here. So the game is now to prevent the fly from accessing the boundary. And of course, we won't be, I mean, we won't be able to do this for an arbitrary ratio of these two circles, but for a ratio going to 1, we will be able to do this. And here's one strategy, in my opinion, the most natural strategy. So and maybe I'll give myself more space. Okay, I think after this I'll stop trying to draw actual circles because it's going to get messy very soon. Uh, take a circle and divide it into n equal parts. In this picture, n will be equal to 6. And now draw circles, maybe I'll make them blue, orthogonal to the initial circle through these points. And since you divided the circle into n equal parts, in fact, there will be a circle that's concentric and simultaneously tangent to all the blue circles. And now if maybe I'll make the circle red now. Now, if you're thinking, these give you geodesic planes in H3, which is in your side of the screen. And now if I'm a fly trapped between the two red geodesic planes, I have less access to the boundary of H3 to the screen, but I still have some access, right? Via these triangular interstices. But now I can fill those in. Oh, maybe blue. So now if I take, these circles give me geodesic planes that are the sides of a polyhedron. It's not a compact polyhedron, but it's a finite volume polyhedron. And as n goes to infinity, it's if you want, it's an exercise in Euclidean geometry that the ratio of the Euclidean diameters of these two circles goes to 1. And so this gives you a right-angled finite volume polyhedron, which you can think of as an orbifold instead of a manifold with systole going to 0. Now, if you want a manifold, you can do the same thing that we did in dimension 2. You can basically you can two-color the sides of this polyhedron. So maybe I should say this is combinatorially what the polyhedron looks like. So maybe I'll use it. Well, okay. In fact, yeah, so again, I'm drawing like a stereographic projection, if you want, of the polyhedron. In the case n equals 6. In fact, these are well-known and well-studied polyhedra. They're the ideal right-angled antiprisms. And again, we can two-color the sides of this polyhedron. Right. Here we go. And then doubling first along the sides labeled alpha, and then doubling along the sides labeled beta will give you a manifold. And in fact, you can describe this manifold. Well, Thurston described this manifold. Maybe I'll draw a picture for so for n equal to 3, so this picture is too complicated maybe for n equals 6, but when n is equal to 3, maybe this polyhedron is nothing but the ideal right-angled octahedron. So the picture like this. And well, maybe I should try to. And the manifold cover that you get looks like this. It's a link complement. This is known as the minimally twisted 2n chain link complement. And the curve that's giving you a short geodesic is the one that's attacking you, that's coming out of the screen and attacking you. So these are examples of cusped hyperbolic 3 manifolds with systole going to 0. And I just want to make a comment that while I presented this as an alternative strategy to Dane filling, in fact, secretly Dane filling is happening. In fact, Dane filling is what's giving you a small systole also in this particular example. The point is that you can take this polyhedron and divide it into I guess 2n pieces that each look like this. Combinatorially, they look like this. Where the angle here, I mean, all angles in this picture are right angles, except for this angle, which is an angle of pi over 2n. And the point is, as you decrease this angle, I mean, what you're essentially what's happening is you're Dane filling this polyhedron. So, I mean, this polyhedron approaches some other polyhedron, which is in fact commensurable to the right-angled octahedron, coincidentally. But yeah, so Dane filling is secretly happening here, and it's, I mean, there's a conceptual reason that the two, if you want, opposite sides of this, the two distinguished sides of this antiprism are getting closer and closer together. And also maybe one other comment is that you can, if you want compact polyhedra with systole going to 0, I mean, whatever that means, you can also Dane fill the antiprism as follows. So basically, you somehow go in the other direction. So you turn ideal vertices into edges. And if you want something right angled, you make the dihedral angle at those edges pi over 2. So now the picture will look like this. So the first I mean this gives you a family of right-angled polyhedra that you can think of as Dane fillings of the antiprisms. The first time you can really do this and get a hyperbolic polyhedron is n equal to 5, in which case you get the right-angled dodecahedron. This when n is equal to 6, in fact, you get the polyhedron that Lobel used to construct the first example of a closed hyperbolic three-manifold, which is why these are known as Lobel polyhedra. And it's again true. Again, I mean, there are conceptual reasons that this has to be true. That the distance between these two distinguished faces has to go to 0. And again, you can color the sides and double and get hyperbolic manifolds with systole, closed hyperbolic three-manifolds with systole going to 0. Just before we take a break, maybe I'll say, so for n equal to 4, the fact that the fact that S4, I mean, 0 is an accumulation point for S4 is due to Hegel in a very beautiful, short, and unpublished note. But in fact, what I mean, Hegel proposed a strategy that was general. It's just that he lacked some. There were some properties of arithmetic lattices in higher dimensions that he, I mean, that hadn't been established yet. But in fact, Hegel's strategy was then pushed into, I mean, all dimensions. I mean, the same argument works in every dimension by independently by Biloli-Petsky, Thompson, and Bertrand, Haglund, and Wise. I think both at the same time. This was, I can't remember when this was, 06. This was 2011. And the strategy, I mean, it's in fact, I mean, all known constructions of high dimensional closed negatively curved manifolds use number theory, somehow employ number theory. And in fact, it's an open question, an open and vague question of Gromov, whether you can construct such manifolds without using number theory. And I mean, these results are no exception. So their strategy is to take an arithmetic manifold and inbreed it. And this is the same strategy we're going to use I'm going to use to prove that not only is 0 an accumulation point, but every non-negative real number is an accumulation point of the set of systoles of closed hyperbolic manifolds. So it will really just be an elaboration on this short note of Hegel. And in fact, our paper is also very short. Okay, maybe I'll stop here.
Okay, thanks, Sami.